When is that thing an aisle? That's actually asking for more here, right? If we have that the intersection of aisles is an aisle, then it's automatically going to be the meet. So we could have something that meets, but that doesn't necessarily intersect to be an aisle. It turns out, so a bit more hands-on though, turns out this is still a really difficult question to answer. Just to give a bit of an idea of just maybe how challenging that might be, is that we don't really at the moment know of a sufficient and necessary condition for that thing. There are some propositions for a sufficient condition. So you have some work by Bondal and also independent work by Broomhead, Plug, Pogstello. Sorry, David, you come first. Pogstello and Plug that give a sufficient condition here. So Bondal does this by what he calls consistent pairs. And these three gentlemen here do it by something they call the refined truncation algorithm. And at the moment, as far as I can tell, that seems to be a bit of a generalization of this consistent pairs business here. Right, so if we have these things, so we have kind of a quite intricate algorithm here. If we can check the consistency of pairs, then we know, okay, if we take these T structures satisfying these things, then their intersection of their R's is going to be an aisle again. But that's by no means we come back to that. Am I making that noise? Oh, okay. All right. So that's by no means a given. So we see that in an example, in the example we're going to present in this talk. Secondly, maybe if we, since we're here, if we come from a representation theoretic intuition, then it's maybe not so surprising that this is a really hard question, and that the answer is probably going to be something like not very often / almost never. And if you think about this in terms of maybe like the abelian category analog, if you think about this in terms of torsion pairs, then you have these results by Ringel, which is based on results result by Yama and Brighton, Thomas, and Todorov. So which states that if you have lambda to be a connected hereditary Artin algebra, so that's what Ringel shows based on a result by Yama, Wright, and Thomas Todorov, which does that for the working over an algebraically closed field. Then you have, and I think the bijection fits the board if I crouch down a little. So you have that the functorially finite, at least, torsion pairs form a lattice. That's too low? Ah, Mama, I can make this little red mark. Wasn't good enough. What? You made it correctly, but then it happens. Oh, well, okay, so someone moved the camera. Okay, functorially finite torsion pairs. Yeah, is that fine? Good. Form a lattice under inclusion if and only if lambda is a thinking type or really small, or like I guess Kronecker, less or equal to 2 vertices. So basically, again, almost never. So it's, if we think of the T structure question to be a triangulated analog of the torsion pair question, is probably not too surprising that maybe we shouldn't expect this to usually happen. Right, so after being so demotivating about this whole business that we just lift our spirits a bit and present a category where this does happen. And it always happens. Any two T structures, well, the whole collection of T structures forms a lattice, and the meet is given by intersection of aisles. So that's the following class of categories: C of Z, Z, and discrete cluster categories of type A, which were introduced by Iguza and Todorov. So that's also kind of where the representation theory is here. That's where the cluster stuff comes in, right? We have this nice cluster algebra that we can understand from a kind of combinatorially cluster theoretic viewpoint, and we can really use this hands-on combinatorics to show that here we have a lattice. And maybe to just already say a little bit, give a bit of a spoiler about this lattice. This lattice is going to be connected to non-crossing partitions of type A. So it lives nicely in this whole type A picture, and which is pretty cool because like non-crossing partitions really show up in all sorts of places. There's, if you're interested in that, and maybe you should be, there's a nice survey by Krause and others really showing just in how different contexts these non-crossing partitions show up. They show up here as well. And in particular, maybe it's worth pointing out that that also means that we couldn't exploit Bondal's result here, which kind of implies some sort of modularity here. And our lattice is not going to be modular usually. Okay, so we have these categories, so let's talk about those. They are associated to a combinatorial pictures like such. So we take some subset of the circle S1, and we want this to be infinite in order to be fun, well, for our goals fun at least, and we want it to be discrete, hence discrete, right? So we're going to put some points on the boundary, and if we put infinitely many discrete points on the on S1 here, then they're going to accumulate somewhere, and have some accumulation points. And what we ask is that each accumulation point is two-sided. So we have a sequence converging to it from both a clockwise and an anti-clockwise direction. Technical condition. Also, in addition, we ask for there only to be finitely many accumulation points. So in that case, we have 3. So n is the number of accumulation points in case I use an n and forget to say what it is. And there's only finitely many. Right, how to associate a category to that data? Well, C of Z, what it's going to be. It's going to be a nice category, and right, I mean, nice is like kind of means the usual suspects. Feel free to mentally compare that to Pierre's list from yesterday. We have a K-linear, home finite, Krull-Schnitt, triangulated, 2-Calabi-Yau category. One important difference to Pierre's list yesterday is that we do not have cluster tilting objects. That would be a problem because then we wouldn't have any T structures. The periodicity of the suspension would prohibit, in that case, the existence of T structures. In fact, we have cluster tilting subcategories, but these have all infinitely many isoclasses of indecomposable subsets. Right. So how do we, can we describe this category in terms of the model? So we have that the indecomposable objects correspond to arcs. And I mean, even if you haven't seen this particular infinite picture, I'm sure like none of these notions will come as any surprise. So an arc is a pair of non-neighboring vertices here, and arcs correspond to indecomposable objects. Then suspension, let's say sigma, right? We have a triangulated category here with suspension sigma, is just clockwise rotation by one step. Right? Each, by virtue of how we set up our discrete set of points here, each point is going to have a predecessor and a successor. We can rotate an arc like such. And that's going to give suspension on in the composables. And we can.
And combination points cannot be included, right?
Yes, exactly. In this case, they're not absolutely not included. That's a very good remark. So there is a model to include the accumulation point where Paquette and Yildirim take these elusive of categories and they complete them under this. But in our case, they are not included. So we have that business, and then the HOMs are easiest to describe in terms of the X. And again, probably absolutely no one is even a little bit surprised. We have that thing is one-dimensional exactly in the case. We work over some field K, I probably didn't see that. So it's one-dimensional if X and Y cross, and it's zero-dimensional else. And right, also like in terms of, maybe again, these accumulation points that might look very familiar from Eleonora's last talk last week, or we had a kind of a setup like that. That is not coincidental. If we look at our subcategory of generically free guys in the case k equals 2, so where we mod out x squared in this ring that Eleonora presented, then the stable category of that is exactly the same as the one accumulation point case here. So we have that set up maybe to just complete the picture. And I think I have the almost full board available to me. So in terms of how these factor, you can loosely, if you translate this condition here into HOMs, non-shifted ones, right? You can loosely translate the HOM into something that forms an angle like that. Like we have the HOM from X to Y. If we have some sort of angle like that, we can rotate X in a anti-clockwise direction to lie on Y. Then this morphism factors through an object S if and only if, when we do that rotation, we have to go through S. So that's the category. Now we can use this very hands-on model to just classify all sorts of structures in this world. And the first thing, maybe slightly obvious thing to note is that throughout these talks, all the subcategories that I'm interested in are going to be full, replete, closed under direct sums, closed under direct summons. So they're just completely described by the indecomposable objects or arcs they contain. So a subcategory in that sense is nothing else than a set of arcs. So we have that subcats are in one-to-one correspondence with sets of arcs. So if I want to give a condition on a subcategory, I can give a condition on the corresponding set of arcs. And now the first thing you want to do is we want to talk about torsion pairs, which you'll remember at least, I mean, from Thomas's talk yesterday, which was working in a humble triangulated category today. But we still can use this idea. So we have X and Y is a pair of subcategories. That is a torsion pair. If, firstly, we don't have any HOMs from X to Y, no non-trivial ones, and we can build the whole category from X and Y. I'm using the notation that David used last week. So what does X star Y mean? It just means everything we can build as an extension from something in Y by something in X. Right. So that's a torsion pair, important to note in case that this is a torsion pair. When we call that the torsion class, the torsion part, the torsion free part, each of those is determined by the other. So if we want to describe all the torsion pair, in fact, we can just describe all the torsion classes, same information, right? Y is just the HOM right perp of X. Okay, so we have the following result, which is joined with Torsten and Peter, which state that such a pair of subcategories is a torsion pair. If and only if, and we can just say what conditions do we need on X on the torsion class. X as a set of arcs satisfies two conditions. And the first one is PTO, which stands for Ptolemy. And we might make you think of Ptolemy relations and type A cluster algebras, and that would be a good thing to think about because that's precisely what the picture looks like. So if we have a pair of crossing arcs in our torsion class, then this forces the convex hull to be in the torsion class as well. And I'm told red is a bad color, but I'm just going to be a maverick and use it anyway. So that thing is then also in X. Right, so that's the first condition. That looks a lot like classifying torsion pairs in finite type A. If you are familiar with that classification, it's element. Second condition is PC, which stands for pre-covering. Here we have infinitely many things, so we have to be a bit more careful about pre-covering. And the PC condition, I'm going to do a bit of a sneaky thing. I'm just going to say this is a simple convergence condition, and it is. It has to do with how the arcs behave around accumulation points. And I mean, you could probably say, Sira, well, if it's so simple, why don't you write it down? And I would say it is really simple, but it's maybe not simple enough for a 30-minute talk. Right. So we have these two things, and they're quite straightforward to check for a set of arcs. That determines that we have a torsion pair. Right, if we start with that, then the only thing you want to add on to a T-structure, again, remember the definition from David's talk, is that such a pair XY is a T-structure. Well, such a pair being a torsion pair. Is a T-structure if additionally the aisle is closed under suspension, or equivalently the co-aisle is closed under co-suspension, desuspension, but that's just what we need to check. So that translates absolutely immediately to our picture. I have it still on this side. Suspension is clockwise rotation. So that just means that this X, this subcategory X, has to be closed as a set of arcs under clockwise rotation. That's a bad place probably to write. Here, closed under clockwise rotation. So you can just, that's the description of T-structures satisfying PTO, PC, and this closure under clockwise rotation. So the question is, what exactly do these things look like? And it turns out they look a lot like non-crossing partitions. Or more specifically, they're going to be classified by decorated non-crossing partitions, which is we just throw in a bunch of points in the topological closure of Z. So have the following result. So maybe let's split that up in parts. So there is a one-to-one correspondence between T structures in our discrete cluster category CZ. And now I probably should have remind you of the N again. N is the number of accumulation points, which we assume to be finite. So there's a projection to Z bar, decorated non-crossing partitions of the set N, which is just a linearly ordered set with N elements. So think of it as the numbers 1 up to n. So what are these things? Let's just stay for a leisurely moment and think about Z-decorated non-crossing partitions. So we have our n accumulation points, and we label them A1 up to AN in an anti-clockwise direction, because that's the direction I choose. And right, what is a non-crossing partition of numbers 1 up to n? It's a partition of that set. So a non-crossing partition is a partition of this set such that the blocks don't cross. And it's really easiest, well, I find it easiest to just visualize it on that picture here. So we're going to connect two accumulation points with a line if and only if they lie in the same block of a partition, of the partition. So let's say we have A1, A3, and AN in the same block. So we have here A4. Then what we do not want to do, we don't want to put A2 and A4 in the same block, because that would result in our blocks crossing. But if you can draw the blocks without them crossing, that's a non-crossing partition. Right, so what is a Z decoration? A Z decoration is so maybe a Z decorated non-crossing partition is a pair P and X is an n tuple. We go with our n accumulation points, and P is now a non-crossing partition of n. We've covered that. And X is just some elements in, Xi is an element in Z bar, in the topological closure. In fact, we want to choose Xi to lie in the interval between AI and AI plus 1. Right, so that's AI and AI plus 1. We want Xi to lie in there. So for each interval, we choose a point. So that thing is in the product of AI plus 1. We just calculate modulo n to make it all make sense. So you notice I allowed for the accumulation points to be included in the decoration, hence we want to really talk about Z bar decorations, but only very rarely. Usually I want this Xi to be slack bam in the middle of this interval somewhere, but not on the corners. I allow it to be in the corners only in two cases: if I is a singleton or if I is an adjacency. So Xi is allowed to be AI only if I is a singleton. And Xi is allowed to be AI plus 1 only if I is an adjacency. That's just for the formal definition. Okay, so the nice thing to maybe observe is that, no, let me observe another nice thing first. So what does that tell us? Not a whole lot if you take me just, you know, by face value. I'm just saying that this thing is in a projection with this thing, and okay, this is a countably finite set, so I suppose we know that we have countably many T structures. I was like, hooray. But actually this is quite a natural bijection, right? So we can, if we write down such a Z decoration and we draw it in our picture, we see the aisle of the T structure. Conversely, if we draw the aisle of the T structure in the picture, we can directly read off the decorations and the non-crossing partitions. I'm probably not going to do that given the time in an example, so I hope you believe me when I say that. What I want to tell you though is that both of these things are partially ordered sets, right? We talked about the order we want to have on T structures. We want to order them under inclusion of aisles. Good, that's an order. These things are naturally ordered as well, just by the product order. I mean, these points are pretty boring. I mean, just ignore them. They just live in linearly ordered sets. right? All good there, nothing to worry about. That thing is a non-crossing partition, poset of non-crossing partitions, famously studied by Creveras. So we just take the product order on this whole business over here. So that's ordered. And in fact, that thing is an isomorphism of posets. This is an isomorphism of posets. Now, ever have had anything to do with non-crossing partitions? I'd be very surprised if you didn't know that this thing was a lattice. This poset structure actually is a lattice, right? So we have meets and we have joins. So if we have an isomorphism of posets here, in fact, we have an isomorphism of lattices. And that's where we have to kind of circle back to the very beginning of the talk. We have a lattice of aisles here. Worth observing, and that's absolutely not automatic, right, from just what I write down here, is that the meet of two aisles is in fact given by their intersection. Or meet of maybe T structures, because I wrote it in terms of T structure. Meet of T structure is given by the intersection of their aisles. By the T structure that's determined by the intersection of their aisles. Right, good. So maybe let me just finish by giving some observations or further results, if I, being honest. So, well, we can kind of look at all sorts of properties that such a T structure could have. It could be bounded, or actually it couldn't. We do not have any bounded T structures in here. We can, and that's kind of nice if we love non-crossing partitions like I do, then the lattice of non-crossing partitions shows up on the nose here. And we see that we have a lattice isomorphism between the lattice of non-crossing partitions and the lattice of equivalence classes of non-degenerate T structures. So non-degenerate T structures, kind of, if you consider them up to equivalence, forget about the decoration. In that specific lattice, you can have a top and a bottom, or you better because it's the lattice of non-crossing partitions bounded. So the top is given by bounded above non-degenerate T structures, so they're all equivalent to one another. Bottom is given by bounded below non-degenerate T structures. And the last thing maybe I want to say is that we can then play around with nice concepts we know from non-crossing partitions, and one thing we know is like the lattice is self-dual. We have this notion of Creveras complement. We can take a non-crossing partition, look at its Creveras complement that flips the lattice upside down, and taking the Creveras complement, you really see it directly here, gonna give you the coaisle, and that's really what you'd expect. So you have this duality of the aisle lattice to the coaisle lattice. But actually the category constructed at the very start is self-dual. It's equivalent to its opposite category. So we expect, since we do have a lattice of T structures, we kind of expect, on the inclusion of aisles, we expect this lattice to be self-dual, and it is. So that's what I wanted to say today. Thank you very much.
Thank you very much. So are there any questions? So I don't know how I should proceed. Maybe first the people in the room could ask questions, and then maybe in the chat.
Okay, it's only a stupid question, sorry. What's the adjacency?
Yeah, that just means that I and I+1 live in the same block.
Definitely I and I+1, right?
Definitely I and I+1, yes.
Do you think this is the only case where lattices will occur?
No, but probably one of the few. Yeah. Probably one of the few. I mean, maybe that's a bit of a bold statement. I do not think it's going to happen very often that the whole thing is going to be a lattice, but I expect there to be more. I mean, maybe there's, what about type D, right? Maybe there's a analogous statement here. I don't know. Haven't looked at that.
Okay, thank you.
accumulation points?
Oh, I mean, to be honest, I mean, we haven't done that, but I expect you can just use the whole technology here to classify everything in the Pocket Yildirim case, and then generalize. I mean, I expect just, you know, you just slightly tweaking the conditions, right? This PC condition is now, instead of having some sequences of arcs, it's going to have accumulation arcs in it and such. But I expect, I mean, like, dangerous last words, right? But like, I expect this fairly straightforward from that.
What is the difference if you have infinite
Again, we haven't done any of these classifications in the case where we have infinitely many accumulation points. I would expect again, but again, I'm being careful saying that. I mean, you have to be a bit careful about how you want to phrase these convergence conditions. Yeah.
I'll just come back to the last question. So I mean, the Yildirim test is not particularly out. So you suggesting you don't need to very strongly?
Oh no. I mean, like, well, I mean, no, we do use it very strongly because we use this specific category very strongly. But what is going to happen, right? You're going to have, if you want to do this extension closure, you're not just going to look at crossing arcs. You're also going to look at two arcs come infinity. You kind of have to think of them as crossing, right? So you have to tweak for sure. I mean, if you want to, again, I mean, I can talking out of hot air a bit because I haven't actually done this calculation. I just expect it to be fairly straightforward. You just want to tweak but I mean, the statement that you actually, oh yeah, that only works in the two Calabi-Yau category. I think that doesn't show up. The statement that show up is like, that only works in this specific category. Well, it's not really because basically, well, I mean, you get just these things, right? Or I mean, you just have to be very mindful of the functorial finiteness thingy. I mean, that's true, but this doesn't really. I mean, again, you have to tweak the conditions, but I don't think anything breaks.
Okay, so.
Oh, I think David had another.
Oh.
Unless.
So there's a huge parallel conversation.
Oh, sorry.
Someone, I think it's so.
I was going to ask if there's a story in other types like type D, but you made an offhand comment that you haven't looked at type D.
Exactly. But I would hope so. I would hope that stuff goes through in type D. I mean, that'd be cool. I mean, if you really then end up with like non-crossing partitions of type D, that'd be sweet.
Maybe ADE all at once with root systems.
Well, E is a bit hard if you go to infinite.
Maybe I have a question. So it's about when you start with a torsion class X and you draw it on the picture, is it easy to see Y topologically?
So how kind of the definition of a torsion class translates to the geometric picture?
Yes.
I mean, I would say it's not unexpected, but it's not entirely trivial, no. That you have to really check things. So you kind of want to use that, it's pre-covering. So that's directly encoded in the PC condition. And then basically what you use is that you can translate the condition that for a torsion class, right, the left perp of the right perp has to be the torsion class itself. You can translate that into a condition that if you look at all the arcs that don't cross anything in X, that's a set, and you look at all the arcs that don't cross anything in that set, then that has to be X again. So you can kind of just sitting down and making sure you can translate that fairly quickly, but that condition is really hard to check for a set of arcs, and that's really kind of where most of the work lies with this result with Torsten and Peter, that you want to translate that this thing plus PC is really the same as Ptolemy plus PC, because this thing alone is not the same as the Ptolemy condition. We really need both to have them be the same as these. So there's some, yeah, there's technical work involved, definitely.
Okay. So if there is no more question, maybe we can thank the speaker again, and we could meet in 8 minutes for the next talk. So thank you very much.